So we would like to give a conceptual description of the group law on an elliptic curve. We said that for all intents and purposes, an elliptic curve can be described through an equation of the form y squared is equal to x cubed plus ax plus b. So this is a curve of the third degree, and one of the consequences of that is that, generically speaking, if we take a line that intersects this curve at 2 points, then it's also going to intersect it at a third point. I'm saying generically because there are some interesting cases in which this does not happen exactly like this. Or there are other cases in which you need to consider the 2 points as being the same point. But in any case, that would already suggest that starting with 2 points on an elliptic curve, we could get a third point. We might want to use this in order to come up with a group law. In general, a group is a set where one can compose two elements and get another element. So for example, many of the natural operations in mathematics define group laws. For example, addition in real numbers does exactly that. So we might argue that we could apply this general principle. However, in practice, it has to be applied in a much more precise way. In fact, instead of considering just all pairs of points with, in general, complex coordinates that satisfy the equation, we actually enlarge a little the set of points that we're considering. So instead of working with all points in a two-dimensional complex space, we work with the so-called projective space. And the projective space consists of all triples of points. So we have something like x, y, z. And the idea is that x, y, z cannot be all zero at the same time. And we also identify triples that are proportional. One could actually describe the projective space as the set of all lines in the three-dimensional space. So, and if we do that, then we can consider every point that of the usual, every point with usual coordinates as being associated with a point that has projective coordinates that look like this. And in general, in order to come up with the kind of points that we're interested in, we replace y by y over z and x by x over z in our original equation. And if we do so, let's do a simple computation here. If we multiply through by z cubed, we will get the equation y squared z is equal to x cubed plus ax z squared plus bz cubed. And what is interesting about this form of equation is that a new point that was not identifiable before in the classical setup emerges. And that's precisely the point 0, 1, 0. So if we plug in x equals 0, y equals 1, and z equals 0, we will realize that both sides of this equation are 0. So one could apply the same principle of attaching 3 points, of attaching a point to 2 points in this setup. And it turns out that this very special point that we found is going to act as the origin of the group, or the neutral element of the group. We sometimes refer to it as the point at infinity. And now we can describe the group law as follows. So imagine that you have the point at infinity somewhere here. So if you start with 2 points, then you find the third point, and then you connect the point at infinity with that third point, and whatever point you find, that is the point you associate with the sum, or that's what you associate with the 2 initial points. So in other words, that is going to be the point A plus B. In fact, it turns out that if you call C the third point that you initially found, then A plus B plus C is actually equal to 0. So that's how we define the group law, but in most cases, we will not have to work with this equation that will be referred to as the projective equation. And we will see that there is one more level of generalization that we need to introduce here. And eventually we will have the complete picture of how things work out with elliptic curves. And that's it.